Hi, everybody. So I'm recording this lecture. This is my lecture for Wednesday, January 27th, 2021. I'm recording it just in case the same thing happens as what happened last time and my screen is all blurry. I haven't had a chance to fully explore that with the IT people yet. So I'm going to record this lecture by sharing my screen, and hopefully I'll actually have a real lecture. Maybe I'll post this one instead of the Zoom one. We'll see. Okay, so I'm going to share my screen and get started. Let's see. Okay. So it looks like the screen is sharing fine. So this is for Wednesday, January 27th. And I hope you had a chance to go over the video that I made for the last lecture, which was only about 45 minutes. And we covered in that, that last time. Let's see. I posted this. It's about 46 minutes. We did the combined gas law, which I had also published a previous video on for you to watch. We talked about Avogadro's law, how volume is proportional to moles. I told you about the ideal gas law. And also we modified it for figuring out molar mass. So we got the equation M equals mRT over PV, where this is now the mass in grams. And this is something that you use in the laboratory. So you'll be very familiar with that. You either are from yesterday or you will be tomorrow. And we also talked a little bit about gas density. And you could also take PV equals nRT. And actually, you would start with this form of it. M equals mRT over PV. And you'll notice that M over V is the density. So you can replace that and get a formula that has a density. And if you solve, anyway, you should watch the other video. I'm not going to go over everything I did there. Okay, so what we're going to do today, another thing I did last time is I assigned graded assignment 1, GA1. It is posted under unit 1, okay, and it's due on Sunday at the end of the day. It has basically 2 problems. It's actually number 10 and number 22 on the activities, but it's on its own sheet. And for number 10, I ask you for an explanation as well. And I give you a space to write it. So please post, submit to Blackboard. And there's a folder for graded assignments that you will find, and that's where you should post it. So what I want to do today, oops, that didn't work too well. What I wanted to do today was talk about how to use the ideal gas law when we have gas mixtures. Okay, and I'm going to start by going over this activity. This is activity 5 from unit 1, and it shows a reaction here. So sometimes gases react, okay? This is a very famous reaction. It's the formation of ammonia gas from nitrogen and hydrogen gases, and it has an interesting stoichiometry, right? Because there's a 1-to-3 ratio here. 1 moles of N2 combined with 3 moles of H2 to give 2 moles of ammonia. Okay, so it says at the beginning of the problem, nitrogen and hydrogen gases are contained in a balloon whose pressure is always equal to atmospheric pressure, and the pressure is therefore constant. Well, let me explain that a little bit. So here we have a balloon, okay, and it contains these N2 and H2 gases. And what you have here is the balloon is made of a very sort of weak and flimsy material. Okay, at least to a first approximation. So what that means is that it really has no ability to contain a higher pressure inside of it. So we say that the pressure inside and the pressure outside are the same because of the material in that flimsy balloon. In the experiment that you do in the lab, some of you did, we did it yesterday, you saw that Mrs. Sayak and I had to do a little work to make the inner and outer pressure in the graduated cylinder be the same, because the graduated cylinder does not have flimsy walls. So we had to adjust the height. Well, I don't want to get too far ahead, but we had to go through a little bit of effort to make the inside and outside the same when we had the graduated cylinder inverted in the water. We had to make the water level the same inside and outside. But here, it's the flimsy material of the balloon that allows the sorry about that interruption, had a little delivery. I had to pause the video. But anyway, so basically what that tells us is that we always know what the pressure is inside the balloon because it's equal to atmospheric pressure. And it says that the conditions here are at standard temperature and pressure, so that the pressure is 1 atmosphere. Let's call it 1.00. And that is the total the pressure inside of this balloon, which is the same as the pressure outside. Okay, so then what happens? It says initially there is 1 mole of nitrogen and 3 moles of hydrogen. I tried to make this problem as simple as possible in terms of the numbers of moles, okay? So I had that reflect their stoichiometric ratio. So it says, what is the initial volume at STP? So we're saying, let's pretend that these gases don't react until we say react, okay? So before reaction, what would be the initial volume, okay? Because of, and then what happens after they react? And that's what we're going to consider here, because when you look at this reaction, you could see that there's 1 mole of N2 reacts with 3 moles of H2. And in the end, you're going to end up with 2 moles of ammonia. So if this reaction goes all the way to the right, so if it goes completely to the right, which I'm saying it does, even though it doesn't really, what happens to the moles of gas? The total moles of gas. You know, we start out with 1 plus 3, and we end up with 2, all right? So we get a decrease in the moles of gas. So what's happening in this reaction in terms of the numbers of moles is it's going down. And now, what are all the things that are necessary to think about when we talk about the ideal gas law? You know, let's talk about what we have at the beginning. So at the beginning, we have standard temperature and pressure, and that's going to stay the same temperature throughout. So the temperature is 273 Kelvin. At the end, the temperature is also 273 Kelvin, all right? The pressure, remember I talked about how the pressure inside and outside will always be the same in this because of the flimsy balloon. The pressure at the end is also 1 atmosphere. So what's changing in this problem is really the number of moles. And as the number of moles change, so moles change, and we know that the volume is proportional to the number of moles. This is Avogadro's law. So as the moles go down, moles drop, right? Because you have 1 plus 3, you have 4 at the beginning, then you have 2. As the moles drop, the volume will drop. Okay, so we're expecting that this balloon will go and shrink a little bit, half, actually by half. So the volume will do that as well. So if I calculate the initial volume, V is nRT over P, and I have 4 moles. And 0.08206 liter atmospheres per mole Kelvin, 273 Kelvin over 1 atmosphere. And let's see, atmospheres, Kelvin. You don't have to do this all the time, but so you see we end up with liters, and we get 89.6 liters. So that's the initial volume. What about the final volume? Well, the final volume is also nRT over P, but the N is now 2. And everything else is the same. So I'm not even going to put in the units. And you can plainly see what's going to happen here. You went from 4 to 2. So this is going to end up being half, 44.8. So this is half of what it was, as expected, right? Because the volume is proportional to the number of moles. All right. Now, it looks like a very straightforward problem. Moles change from 4 to 2, but I kind of pulled a fast one here. Okay, I actually assumed something about gases that I never justified. Okay, there was really an implicit, so I didn't tell you about it, but there was an implicit assumption, although it all made very logical sense, right? That the moles, the total moles of gas would determine the volume. But the implicit assumption that I made was that when you have a gas mixture, so in a gas mixture, we can use the total moles of both gases, right? We had 2 gases present. So in a gas mixture, we can use the total moles of all gases present in the ideal gas law. So we actually did this. We found the volume was N total RT over P total, or P total is N total RT over V. So this is really what we assumed. We assumed that you can add up the moles of each component of the mixture, each portion of the mixture. In this case, it was the nitrogen portion and the hydrogen portion. Okay. In fact, it turns out that's true. This is, in fact, true. And I guess I could say there is an ideal gas law for total moles relating to total pressure and that's number 1. And there are ideal gas laws for each component where the moles of that component relates to the pressure of that component of the gas. And this pressure of that component of the gas, we call this the partial pressure of a gas in a gas mixture. Okay, so what do these relationships look like? They look just like the ideal gas law. P total is N total RT over V. And then we had, say we have 2 gases. Let's just call them A and B. PA is NA RT over V. And PB is NB RT over V. So we can use the ideal gas law for total moles and for moles of each. And we call each of these partial pressures. So what is the partial pressure? What does it mean? What does partial pressure really mean? So the way I like to describe this is I say that the partial pressure of a gas in a mixture is the pressure that gas would exert if it was the only gas there. Okay, so the partial pressure of a gas in a mixture is the pressure that gas would exert if it alone were present. So I always like to illustrate this just by drawing a little picture. Okay, so here's a volume. And what I'm going to do is pretend that I have the same volume. But what I'm going to do is I'm going to draw a bunch of, so let's say gas B is black, and I'm going to put 15 dots in here. Right, so I have that amount of gas B, and let's say I have much less, 5 dots of gas A. So this is A, and this is B. Okay, and now I have the same container over here. This is a certain volume, V, okay, is the same container, same volume, V, but now I'm just going to have gas A in it. Okay, so the pressure that this gas would exert if it alone were present is simply the moles of A times RT over V. So that is the partial pressure. And it's what this gas would exert if we took out all the other gases, which is, of course, not too possible to do. And the same would be true for the other gas. So it's the same volume, V. And now I have, 15. And the pressure here, PB, would be NB RT over V by the ideal gas law. That would be the pressure if it was only gas B. So the thing is that a gas exerts a pressure in a container regardless of whatever else is there. It's going to exert the same pressure whether you had another gas there or 6 other gases there. It really just depends on the amount of that gas that's present. Okay, so so then what about the total pressure? Well, the total pressure is going to be the sum of the 2 partial pressures. And this actually has a name. This is called Dalton's law of partial pressures. But you don't really need to know that. You just need to know that you can add together those partial pressures and get the total pressure. So that means that P total is, okay, so PB was NB RT over V, and PA was NA RT over V. So I can add these together because both of them, I can factor out right? I can do that. But what is that? Well, this is just N total. So this is N total RT over V. Okay. So anyway, this all fits together. It all works together. So whenever you have 2 or more gases that are present, we talk about the pressure due to gas A, and we call that the partial pressure of gas A. And we also have the pressure due to gas B, which is the partial pressure of gas B, PB and PA. Okay, and they add up to the total pressure. So, so in fact, it's really the moles that determines the partial pressures. We could say that the partial pressure of A, PA, is to P total as NA is to N total, okay? Which means that mathematically you could write that PA over P total is Na over N total. But how can I prove this? I mean, I can just assert that, but how do I mathematically prove it? Very easily. Because PA is Na RT over V, and P total is N total RT over V, and everything cancels except those moles. This cancels, this cancels. So this is Na over N total. And of course, what I just did here, which I should have probably written, was PA over P total. Okay, so I've just proved this relation. Okay, so the portion of the pressure that's due to A with respect to the total pressure is the same as the portion of the moles, that's A with respect to the total moles. And actually, PA over P total, okay, I call this Na over N total, but this is actually what we call the mole fraction of A. It's the moles of A divided by the total moles, and we give it the symbol X. So now we have this relation that actually simplifies calculations sometimes, otherwise I wouldn't bother with it. We have this. So the mole fraction of A is the ratio of the pressure due to A to the total pressure, which means that P total times XA is PA. And sometimes we can use, or we could do this with B as well. And sometimes this makes some partial pressure calculations a little bit simplified. And I'll show you that in an example. Okay, so I'm up to the example. This is the application of the law of partial pressures. Okay, so let's say we have a mixture of nitrogen and argon, two gases, and there's 15 moles of nitrogen and 5 moles of argon. And the volume is 500 liters at 298 Kelvin. So what is the partial pressure of each component and then the total pressure? So, okay, let's just do it one way, and then I'll show you how maybe it's easier to do it another way. So if I want to calculate the total pressure, I just use the ideal gas law for total moles. Okay, the total moles is 20. I have 0.08206, 298 over 500, and that comes out to 0.978 atmospheres. That's P total. And now I can do the same calculation basically, but for argon and nitrogen. So PAR is NAR RT over V. So instead of 20 here, I have 5, and everything else is the same. All the other conditions, they're just exactly the same. And so I get 0.245 atmospheres. And that's PAR. And then PN2 is NN2 RT over V, which is 15 times 08206, 298. There's a lot of writing with doing it this way. And you end up with the partial pressure of nitrogen being 0.734 atmospheres. Okay. All right. Now, look what I did here. I did 3 identical calculations, a lot of writing. Maybe there's an easier way, and there certainly is an easier way than that, okay? So what is the easier way? Well, once we have the total pressure over here, we know that P total, so this is an alternate way. We have P total is 0.978. And we know that we have 5 moles of argon and 15 moles of N2. All right, if you add that up, that's 20. We knew that. So we know that we can use the mole fractions, right? The mole fraction of argon is 5/20, or 0.250. And the mole fraction of nitrogen, well, I don't even need to calculate this way, right? I can just take 1 minus 0.250 and get 0.750, okay? Keeping the 3 sig figs. And then I could find the partial pressure of argon as the mole fraction of argon times the total pressure. So that's going to be 0.250 times 0.978 atmospheres, which gives me precisely the same answer, which is 0.245. And the pressure of nitrogen is xn2 times P total, or 0.750 times 0.978, which of course gives me the same answer, or it should. Okay, so, you know, that brings up an easier way to do some of these calculations. So what I'd like to now do is some stoichiometry problems, or let's take a look at stoichiometry problems involving gases. Okay, so of course we have gases that are involved in many chemical reactions. They can be involved as reactants, as products, or both. And in many cases, we're using the ideal gas law to do these problems to find maybe the volume or the pressure of the gas produced. And also we could be calculating the moles of gas reactant that would be needed, all kinds of different things. So many different types of stoichiometry problems. You might want to get, like I said, pressure or volume of a product, gas, or you may want the initial moles. There's lots of different types of problems. There's lots of different variations. So I'm just going to start with showing you an example. Okay, so this is a stoichiometry problem. Let's take a look at it, because it's been a while probably since you thought about some of these things. So, okay, so 525 milliliters of a 2-molar HCl solution reacts with excess calcium carbonate, which is a solid, and it produces carbon dioxide gas collected in a container. Now, obviously, if you have HCl reacting with calcium carbonate, you're not just producing CO2. So what is the reaction here that actually happens, and how does it happen? So it says it's collected in a container. So it's a little bit vague about that, but I would assume it's something like, you know, you have this reaction happening. You have some calcium carbonate here, which is a solid. And maybe this is now covered. So you have some kind of stopper here with a hole in it. Okay, and then you got a gas tube that leads to some kind of container. I don't know. Anyway, a crude drawing there. But anyway, so you get this bubbling, goes into the container. Okay, and you know, I guess actually, this is a problematic drawing, which is probably why I didn't draw it in my notes, because we'd have to worry about the volume here. But let's assume that the container is sort of right on top of this. So we have the container right. Let me make a little space here. I'm getting myself in trouble. So let's say the container is right here. All right, that's better. And here's this stopper that has that. Okay. So anyway, what's happening is we have calcium carbonate reacting with HCl. Calcium carbonate's a solid, and we have aqueous HCl. So this is an acid plus a carbonate, which is one of the reactions that usually we go over in Chem 103. And the products are carbon dioxide, water, and calcium chloride. Okay, just put the phases there to save a little room, okay? And what about the stoichiometry of this problem? Well, the stoichiometry is really pretty simple. You have two H's here, so I have to put a 2 here. You have two Cl's, now that's balanced, but everything else in this problem is 1, okay? So we have a pretty simple stoichiometry for this one. So the first part of this question is asking how many grams of CO2 are produced. So what we're going to do here is we know the molarity of the HCl, and we know the volume of the HCl, which we have to put in liters. We're going to use this to get the moles of the HCl. Once we have the moles of the HCl, okay, we're going to use the stoichiometric ratio. So the stoichiometric ratio is how we're going to go from moles of HCl to moles of CO2. And CO2 is the only gas that is produced. So it's the only thing that's going to determine the volume, or whatever it is. It's going to determine the pressure. We want to find out the pressure in the container. Okay. So, all right. Once we get the moles of CO2, we're going to get the grams of CO2. Okay. All right. So I have the problem rewritten here. And so we'll start with converting this milliliters to liters. So we have 0.525 liters. Molarity, as you remember, I hope you remember, is moles per liter. And that's how we'll get our liters to cancel, and we will end up with the number of moles. Okay, so we have 1.05 moles of HCl. We go back to the stoichiometry. 2 moles of HCl give you 1 mole of CO2. So we have to remember that. 2 moles HCl, 1 mole CO2. So if I were to multiply this out right now, I'm going to actually do that. You would get 0.525 moles of CO2. And now, so then we have to get the grams of CO2. And the molar mass of CO2 is 44. Let me get a decimal place here. I think it's 0.01. And this comes out to 23.1 grams. So really nothing we use in this problem had anything to do with the gas laws. This problem could have been done in Chem 103. But now is a further question here. It says, if the volume of the container is 21 liters and the temperature is 26.0 degrees C, what is the pressure of the CO2 in the container? Okay, so now I'm going to use those things. Temperature is, okay, 26 degrees C, so we have to convert that to Kelvin. And we need to use a decimal place because we have a decimal place here. So it becomes 299.15, which we could round that to 299.2 because we only have one decimal place here. And so now we're going to use the fact that the pressure of CO2 is the moles of CO2 times RT over V. And here's V, here's T. And the moles of CO2, well, we got that earlier. It's 0.525 moles of CO2. Now, in problems like this, a lot of times students will figure out the moles of all the products. I've seen this many times. Students will calculate the moles of this, the moles of this, the moles of this. But the moles of these things has no relevance to the problem. that stuff is actually going to be left behind over here, or, it's not going to go up into the balloon or whatever the container is. So what really matters in determining the volume is the gas that's present. So only the gas produced matters. Okay, so we're just going to take and take our moles, R, T, over 21 liters, and it comes out to 0.614 atmospheres. Okay, and that's the pressure of the CO2. Okay, now sometimes in gas stoichiometry problems, or sometimes when you're doing a reaction where you're collecting a gas, you do something called where you collect the gas over water. So let me stop this for a second. Okay, so very often gases are collected over water. And that introduces a bit of a complication to this type of problem. Because whenever you collect a gas over water, you have to worry about the pressure of water vapor that always exists above a sample of water. So hold on a minute. So for example, okay, here, let me just draw a picture. We're going to talk about this reaction. Zinc, solid zinc plus hydrochloric acid to give H2 gas and zinc chloride. I could say, oh, you've seen this reaction in Chem 103, but of course everybody did online lab last semester, so you couldn't. But this is a metal plus acid. This is an active metal, so it reacts with HCl. It produces, it's actually a redox reaction. The zinc has 0 oxidation state here. It's a neutral metal, but over here it's +2. So it's losing 2 electrons, which are picked up by the H's and form H2. Anyway, so H2 is the gas that's going to be collected, and you could run this experiment by taking a test tube, a large test tube, whatever, with a stopper that has a hole in it that you could put a piece of tubing through. And then you could take this, okay, you could take and invert something like a graduated cylinder into a pan of water, and the water would fill the cylinder, right? We know that that happens because the atmosphere is pushing here. It's pushing the water up the cylinder. So we could take our tubing and put it underneath this cylinder. Okay, so now we have the reaction. We have our zinc, here's a solid zinc, and we have HCl, and we're getting bubbles of hydrogen that are coming up this tube and down it and are going to collect in here. So this is what it looks like initially. Okay, but then after a while, as that gas collects, oh man, I got to draw this whole thing again. Okay, so this thing is full of water initially, but then as the hydrogen gas comes into the cylinder, now we have H2 gas here, and the water level doesn't go completely up the tube anymore. So the gas collects here. Why does it collect here? Because it's lighter, it's got less dense than water, okay? So of course it's going to be on top. So you'll end up with the hydrogen gas there. So now what you have in here, so what's in here, right? What's here? Well, obviously we have H2 gas, but we also, because we have water here, we have H2O gas. We have some water vapor. So whenever you collect a gas over water, you have to worry about the fact that there's water vapor in there as well. Now, it's okay. So I'm going to get back to that. But first, I'm going to solve this problem as far as I can get. Okay. So actually, I haven't given you the problem yet, but now I'm going to give it. So I'm going to work on the problem, and then I'll come back to the water vapor. So let's say we have 2.41 grams of zinc, okay, that reacts with excess hydrochloric acid, okay. The temperature is 25 degrees C, and that's 298 Kelvin. And the volume, so let's say that this volume is 1.80 liters. The volume of the hydrogen gas, 1.80 liters, okay? Of course, there's water vapor in there as well, but. So what do we do? What do we have to do? So what is the goal in this problem is, let's see. Suppose we want, what is the final pressure? Over here. And hit this thing. Okay, so how we're going to do this problem is we're going to take our grams of zinc, we're going to convert it to moles of zinc. Then we're going to use the stoichiometry of the problem, which is like this, to get the moles of H2. And because we have a 1-to-1 mole ratio of zinc to hydrogen, these are going to be actually the same. The moles of zinc will equal the moles of H2. Okay, then we're going to use the ideal gas law. All right, so let's go ahead and do this and to find the pressure. So the grams of zinc is 2.41 grams. The molar mass is 65.38 grams per mole. And that gives us 0.0369 moles of zinc. And because we have a 1-to-1 ratio of zinc to H2, that means the same number moles of hydrogen. Now, there are plenty of problems, stoichiometry problems, where you'd have to use the mole ratio there, but this isn't one of them, okay? So this is now N, okay? So P would be nRT over V. But hold on, right? We have two gases that are present there. Because we know that we collected over water. So we have a pressure of water, which we call the vapor pressure of water. And then we also, of course, have the pH2. And actually, we know how to calculate the partial pressure, the pressure that's due to H2, from the moles of H2, which is what this is. And we can easily do that. So that's what we're going to do first. We're going to get 0.0369 moles times 0.08206 times 299, right? No, 298 over, hold on a sec, 1.80 liters. And this gives me 0.501 as the partial pressure of water. Okay, oh, sorry, of hydrogen. But P total is going to be pH2 plus pH2O. And what am I going to do about this? Okay. Well, it's really not that big of a deal. The reason is because at a certain temperature, the partial pressure of water is a constant. The vapor pressure above water, the vapor pressure of water above liquid water, as long as the temperature is constant, it's just a number that you can look up, okay? It depends on temperature. And this is something that we're going to study in detail in the next unit, but just so you know, right, here's a bottle. Here's got some water in it. I close the bottle, okay? Let's suppose the temperature is, 25 degrees C. If I leave this bottle closed, what happens is, there's some gaseous molecules, and there's actually the process of going from liquid to gas and gas to liquid that sets itself up in this closed container. And so this is the vapor pressure, pH2O, at 25 degrees C. Now, what would happen if you heat this up? When you heat up a pot, it's not closed, but you could see that there's more and more vapor above that pot as you heat it up. And if you're in a closed container, that becomes a fixed number. So if you heat it up to, say, 65 degrees, or let's say 70 degrees C, so now you actually have more molecules. So more H2O gas. Okay, so the partial pressure of water is greater. Okay, but these are numbers that we can look up. They're in tables. In fact, I have a table here for you. Let me move it a little bit. Oh, man, I was really off. Okay. So here you could see at 25 degrees C, the vapor pressure of water, pH2O, is 23.8 torr, or millimeters of mercury. Okay. As it goes up, here's 70. Look what happens to that vapor pressure of water, 234.1 torr. And here's a very unique situation. At 100 degrees C, which is the boiling point of water, the vapor pressure of water is 760. What is 760? That's 1 atmosphere. This is the same as atmospheric pressure at sea level. And that's why this is the boiling point. And this is something we also learn in Unit 2, that the boiling point of a liquid is the temperature at which the vapor pressure increases enough so that it actually equals atmospheric pressure. And that's why those big bubbles that form do not collapse, because they have a high enough pressure to be sustained. And that's why you get the bubbling action. But that's not really what I'm talking about here. Here, what I've just figured out is that at 298 Kelvin, which is 25 degrees C, the vapor pressure of water is 23.8 torr. So now all I have to do is I have to add that to this number that we got earlier, right? 0.501, but this is atmospheres. Okay, well, that's not a big deal. I'm going to convert my 0.501. I'm going to convert that to torr. And when I do, it comes out to 381 torr. So that's pH2. And pH2O is 23.8. Add that to pH2. And the sum is 405 torr. And that is the total pressure. If I wanted to convert it to atmospheres, I could, but I don't have to do that unless it's asked. And that comes out to 405 over 760, or 0.533, which is the total pressure. Okay, so if I were in class, I would put you in breakout rooms and have you work on problem 20, problem 22. This is actually in the graded assignment. And problem 23, these are all stoichiometry problems involving gases. This is not over water here, 20. And so I would, I'm going to post the solutions to these. And I also want to tell you that I would like you to watch a video before class next week. It's on the kinetic theory, the last topic that we study, and gas speeds. And I post these videos sometimes, this has more detail than I will have time to cover in class. And it's got some overlap for sure with Monday's class. And but anyway, it'd be great if you watch that before class, because then you'll really be ready for class. And I do that I really don't want to have to talk continuously for 2 hours on my lecture days, or even an hour and 50 minutes. I'd like to free up some time for breakout groups and things like that. Okay, so I think that's it. That's it for this video and this class. Bye-bye.